Hello and welcome back to the National Solar Observatory for the second instalment of our Eclipse Preparation Webcast. Today we're going to be looking into the layers of the Sun. During the solar eclipse, we can expect to see one layer really prominently, and that's the solar corona, or the crown, which is the outer layer of the Sun's atmosphere. But the Sun is really complex, and it has lots of different layers with very, very different characteristics. So one of the more interesting things about the Sun is it doesn't actually have a surface. Even though when we look at the Sun and it appears to be a nice ball in the sky, it looks like there is a surface to it. That's just the way the gases in the Sun are behaving. When you look at the surface of the Sun, which you shouldn't do without adequate eye protection, otherwise you might cause yourself some serious eye damage, it's a bit like looking through a cloud of fog. If you're driving towards a fog bank, it looks like you can't see anything through it. You know that once you hit that edge of the fog, nothing much is going to happen to you other than your visibility will change. So the same is true of the Sun, with the exception of the very high temperatures, of course. But if you were to somehow magically drive through the surface of the Sun, you wouldn't hit a hard surface like the ground that we have here on Earth. It's just the gases change their characteristics. So the same way as when you look at a bank of fog and you can't see through it, you don't know what's behind it, we look at the Sun and we can't see what's inside of it. However, scientists use some really interesting techniques called helioseismology to actually study inside the Sun. Even though we can't see it, we can use sound waves to probe the inside of the Sun and to understand what's happening in there. We're going to find out a little bit about that later on this afternoon when we have Dr. Frank Hill, who's going to tell us about his helioseismology program. So the Sun has many different layers, so we're going to start at the inside and work our way out today. The innermost layer of the Sun, we call that the core. At 15 million degrees, the core of the Sun is by far the hottest internal layer of the Sun. It's also the most dense, and that means that it has the most number of particles packed together of any internal layer. It's about 15 million degrees in there, and it's powered by what we call nuclear fusion. This is where the Sun's energy originates from. Taking two hydrogen atoms and pushing them together to form helium, this process of nuclear fusion results in a huge amount of excess energy. The energy equivalent of about 10 billion megatons of TNT is produced in the core of the Sun every second. So once the energy is produced in the core, it has to go somewhere. The core of the Sun is about a quarter of the solar radius. Once you get to the edge of the core of the Sun, the next layer out is called the radiative zone. The radiative zone is a fairly thick layer above the core but below the surface of the Sun. Once energy and particles of light leave the core of the Sun, they have to travel through the radiative zone to get towards the surface. What's interesting though is it takes almost 100,000 years for a particle of energy or light to travel from the core to the surface. And the reason for this is as it passes through the radiative zone, it can only go a very, very short distance before the energy gets absorbed by another atom and then gets re-emitted in a different direction. So instead of traveling in a straight line from the core to the surface, it ends up doing what we call a random walk. That means that the light that we see coming off the surface of the Sun today was produced in the core of the Sun up to 100,000 years ago. So we're looking back in time. Once we get to the outer edge of the radiative zone, we meet a very unusual layer called the tachocline. And this is like a boundary layer between the radiative zone and the convective zone, which is the next layer out. The reason that the tachocline is important is that inside of the tachocline, so in the radiative zone and the core that we've already discussed, the Sun behaves almost like a solid body. It rotates as a single entity. However, once we get beyond the tachocline and go into the convective zone and the surface, the Sun starts to rotate more like a fluid. So where this fluid Sun meets the solid body Sun, we have a layer of very complex science called this tachocline. We also suspect that the tachocline might be the layer in which the Sun's magnetic field is generated, but we'll get to that next month. As we mentioned, the layer above the tachocline is called a convective zone. And this is the region that brings us to the surface of the Sun, or what we know as the surface. The convective zone behaves much like a pot of boiling oatmeal or soup. What we see are patterns called granules that show that material at the bottom layer of the convection zone, where it's hottest, are rising up to the surface of the sun, which is the top layer of the convection zone. And then we can see these cells, these granular cells, moving across, and then the cool gas falls back down again to the bottom layer where it's heated, and then it rises back up. So this convection pattern is really what indicates that we've gotten to the surface of the sun. And we can see these granules on the surface. We see them as large bubble-like features with dark regions in between. So this top level of the convection zone that we've discovered is what we call the photosphere, literally the light sphere. And this is what we recognize as the surface of the sun as we know it. The reason that we recognize this as the photosphere, or as the surface, is that the internal layers are opaque, but the external layers above the photosphere are transparent, so we can see through them. So this is the layer where this transition happens. We found out earlier that the core of the sun is 15 million degrees, but this surface of the sun is only between 5,000 and 6,000 degrees, which comparatively is much, much cooler. In addition to the granules that we can see in the photosphere, this is also where we can see things like sunspots. If you've been fortunate enough to get your hands on some eclipse glasses, you can actually use these glasses to look at the sun safely, even if there isn't an eclipse happening. Just be careful to put your glasses on first before you start to look at the sun. If there are large enough sunspots, usually about the size of the Earth by comparison, you might be able to see them with your naked eye. Once the light and energy particles get to the surface of the sun, they're then free to propagate into space. And these photons are what we receive at Earth and what we see as the sun shining in the sky. It takes about 8 minutes for the light from the photosphere to leave the sun and to reach the Earth, which means that if something was to happen to the sun, we wouldn't know about it for 8 whole minutes. It also means that we're looking back in time a little ways. The sun that we see in the sky is actually the sun of 8 minutes ago. So now we get into the region of the sun that we're likely to see during the solar eclipse. We're going to see from the surface and outward. The lowest layer of the solar atmosphere, closest to the surface, is called the chromosphere, or literally the sphere of colour. During an eclipse, this can sometimes be a really interesting region. This is where we might see prominences off the edge of the sun, as you can see here. The chromosphere has significantly fewer atoms in it, which means that during normal conditions, it's almost invisible to us because it's dominated by the photosphere, which is far more dense. However, once we cover up the photosphere during a solar eclipse, the chromosphere can now really shine bright, and we can see a lot more detail than we ever could while the photosphere was on show. One thing that's very unusual and that we still don't have a good explanation for is the fact that once we leave the photosphere and move out towards space, the temperature that we see on the sun is actually increasing. So it's getting hotter the further away from the sun that we get. And we start to notice this in the chromosphere first of all. If you've had the benefit of looking at the sun through a H-alpha telescope, or during the solar eclipse once the photosphere is covered, you'll notice the chromosphere by its red material that's protruding from the edge of the sun. This sphere of colour can be very beautiful and really interesting during a solar eclipse. Once we leave the chromosphere, we again reach another boundary region called the transition region. Compared to the thickness of the other layers of the sun, the transition region is really, really thin. It's only 100 kilometers or so thick. But what's very strange is that in this really narrow region, the temperature and the density of the sun changes dramatically. So we go from about 10,000 degrees on the chromosphere side of the transition to 1,000,000 degrees on the corona side of the transition. So this is a huge jump, and we don't really understand the reasons for this jump, although it's definitely a question on a lot of scientists' minds. Above the transition region is what we really expect to see during the solar eclipse. This is the corona, or the sun's crown. This is a spectacular region that's dominated by magnetic fields, and plasma is trapped on these magnetic fields, which gives it spectacular structure. The shape of the corona changes over periods of decades. So this period is called the solar cycle. The 2017 solar eclipse is going to be during solar minimum, so we expect the corona to look something like this during the 2017 solar eclipse. The corona is also where we see features such as coronal mass ejections begin to show. Although they originate close to the photosphere, the corona is really where we see them first because they're rapidly expanding. But we'll cover coronal mass ejections and solar flares in a later webcast. The outermost layer of the sun's atmosphere is called the heliosphere, and really this is stretching all the way out past Pluto. So we live in the bubble of the heliosphere. We live in the atmosphere of the sun. Alright, it's time for our Eclipse Tips segment. Today we're going to be building a small handheld eclipse model using the Sun and the Moon. This is based on an activity that was developed by Chabot Space and Science Centre that we have adapted somewhat. You can download the activity from www.nso.edu/eclipse 2017/webcasts/eclipse in your hand. So we begin to build our model using the templates that you can find on the NSO webpage that you can see linked here. We start off by cutting out the internal layers of the Sun. We have the core, then we have the radiative zone, and we have the convection zone. Once you have your internal layers cut out, you want to paint them or colour them in some way. You can do whatever you like. I used orange, red and white, but you can use whatever colours you like since we can't see these with our eyes, so whatever colour we use will be imaginary. So now that we've cut out and coloured in our internal layers, it's time to bring in the photosphere. We learned earlier on that the photosphere is what we consider the surface of the Sun. So that means all of the layers above the photosphere are transparent, so we can see through them. And that means that we can see the photosphere, and all of the layers that are inside of the photosphere are opaque to us. So now we add some details onto the photosphere. So I'm just adding some sunspots here, some little details so as we can tell what it is. So far we have put together the internal layers of the Sun, which are disguised by the photosphere, and now we're going to do the external layers, the chromosphere and the corona, which are the two layers that we expect to see during the solar eclipse. So you can begin by cutting out the templates that we have online, and we'll start with the chromosphere, which is the next layer above the photosphere. So this is fairly close to the surface of the Sun, but we can still see some really interesting features, such as loops and prominences protruding from the edge of the Sun, especially during a solar eclipse. Once our chromosphere is finished, we're going to place our photosphere over it just to make sure that it's completely covered, it's all coloured in. You of course can colour in the entire chromosphere if you wish. I just did the rim since that's what's visible to us. And next up we have the corona, the outermost layer of the Sun. So the key to the corona is that you want to make sure that it looks like it has structure. We want to make sure that we can see streamers and magnetic field-like objects protruding from the center of the Sun. So here I've just used a variety of different colored markers to achieve that effect. Okay, so now we have cut and colored all of our layers of the Sun, and now it's time to put them together. So we have the chromosphere that goes on top of the corona, and then we're going to place the internal layers on top of that, because in just a moment we're going to cover all of that with the photosphere. So that means that the external layers, the photosphere, chromosphere and corona, are visible normally, and then if we lift up the photosphere, then we can see that the internal layers are visible, but normally they're disguised by the Sun. So when we lift up the photosphere, there are internal layers. So of course what we're doing here is exploring how we get a solar eclipse. So in order to do that, we need to have the moon. So we have this moon to scale also on our webpage. You can print and cut that out. And then we're simply going to attach something rigid, such as a coffee stirrer or a popsicle stick, to the back of the moon and to the Sun. And in this way, we're able to move the moon in front of the Sun and actually create our model. Another option for the corona, since it's somewhat tedious to cut out, is to use black paper and some paint. So we trace out roughly the size of our photosphere to make sure that our corona will be the correct size. And then we use paint to create our corona. So the same as before, we need to make sure that the corona is structured and that it's got a linear feel to it, with the sides slightly bigger than the top and the bottom. Then we just do what we did earlier on. We have our internal layers just disguised by the photosphere, and we have our chromosphere on top of that. And then we glue that in place in the center of our corona. Since we're not using the corona template, we're just going to stick a little label on here, or you can write corona on the piece of paper directly. And then we bring in our moon and we have our model of the sun and the moon, and this will give you a very clear idea of what to expect during the solar eclipse. Okay, next up we have a special guest, Dr. Frank Hill, who's from the National Solar Observatory and is the director of NSO's Integrated Synoptic Program, or NISP, who's going to tell us what he knows about the importance of studying the sun in multiple wavelengths. Over to you, Frank.
So, hi, my name is Frank Hill. I'm a staff member of the National Solar Observatory, and I'm here today to tell you a little bit about the layers of the sun. I understand you had a little bit of introduction to that. And, as a quick review, the most visible layer is the photosphere. As you can see on the diagram, this is where the sunspots are located. It's where almost all of the energy, the heat, and the light comes from that keeps us nice and toasty warm here on the Earth. And it's by far the most visible part of the sun. During an eclipse, though, the next year, you'll be able to see two more layers. One is called the Chromosphere, and the other one is called the corona. So here are two pictures of eclipses. That shows you what you will see, approximately, not exactly like this, of course. On the left, you can see the corona. It's very faint. It's only visible during total eclipses because the moon blocks out all the bright light from the photosphere. And in this picture, you can see some streamers. You can see some location of some loops, and there'll be a complex. That's the most beautiful thing that you're going to be seeing during the eclipse. On the right, you can see a picture that shows you the chromosphere as this thin red colored rim right around the edge of the sun. You may be able to see bright spots, which are basically valleys on the moon. They're sometimes called Bailey's beads, and they may also be visible during the eclipse as well. So you might be asking yourself, just why is the chromosphere red? Well, why is it a different color? Well, there's a couple of things going on here. First of all, the different layers of the sun are all different temperatures. The photosphere has a temperature of about 10,000 degrees. The chromosphere is typically a little bit cooler than the photosphere at about 7,800. The corona is at a much higher temperature of 500,000 to 3.5 million degrees or so. There are even higher temperatures present during flares for very brief periods of time on the sun as well. In addition to the different layers being different temperatures, they're also made out of different stuff. So there's atoms from different elements like iron, sodium, calcium. You may be surprised at this, but there's all the elements up to uranium are actually present in the sun itself. So you have a combination of different temperatures at these different layers, and you have these different atoms in different amounts, and so you get a pattern of colors in the sunlight that you can actually use to study the characteristics of the layers of the sun. And it turns out that the temperatures in the chromosphere, the most common element, hydrogen, produces a red light. So it's just the combination of that temperature and that atom being there that produces a red layer called the chromosphere. So this picture is a picture of what can be called the barcode of the sun. You go to the grocery store these days, or basically any store these days, and everything has a barcode of vertical bars of various thicknesses and spacings, which basically has the information of what that object is and various other things encoded in it. Well, this turns out the sun has the same thing. You can only see it when you take the spectrum of sunlight, which means you have to break all the white light into colors. You probably, when you were in school, you got a prism and sunlight, and you were able to make all the colors of the rainbow. We have devices that can spread the colors out over a very long distance, and so we can see a lot of detail. This is called the solar spectrum, and this is a picture of what that looks like in the visible that we can see with our human eye. And you can see there's a lot of dark lines, a lot of patches in there, little straight lines, sort of blurry patches here. And those lines are all caused by the presence of the stuff in the solar layers, the atoms of the various elements. The appearance of those lines, are they thick, are they thin, where are they, how dark are they? All of that contains information about the characteristics of the layers of the sun in terms of temperature and many other things as well. So this is how we get all of our information about the sun, and indeed everything, all the stars in the sky, have their own individual barcode, which will look different from the sun's because they're different stars. The colors in the sunlight are continuous in nature. There's trillions of them, so you cannot actually give them all names like red and blue and green. What we do instead, scientists give them a number, which we call a wavelength. And we can make pictures of the sun in very specific wavelengths or colors using our technology. So solar scientists can make pictures of the sun in very specific wavelengths or colors, and this even extends to colors we cannot see with our eyes, such as radio waves, X-rays, ultraviolet, infrared, and I will show you some examples of the sun in those colors later. We can choose that wavelength so that we can very precisely choose a layer in the solar atmosphere that can be studied. And if we make pictures in the different wavelengths and different colors, you will see very different structures depending on the temperature of the selected layer. Here we have pictures from National Solar Observatory instruments of the photosphere and the chromosphere. Photosphere is on the left, and on the right is a picture of the chromosphere, and you can see these look very different, these pictures. You can see on the photosphere it's more or less flat except for the sunspots that you can see there, and the chromosphere shows you light bright areas as well as long thin elements that look like thread. Those are the filaments, actually. The thread-like structures are the filaments. Anyway, those bright areas are usually around sunspots, as you can see by comparing the position of those bright areas with where the sunspots are in the photosphere. But you can see right there, you will now already have more information about the sun because you have these different looking pictures. So those are just two examples. The next picture shows 9 more examples. And these are all from a spacecraft, a NASA spacecraft called the Solar Dynamics Observatory. And they're all gaily colored, which is done by us. These are not the real colors that you see in the sun. We use colors here because these particular images are in wavelengths that you cannot see with your eye. So we color code them so you can identify them. Color is only relevant for wavelengths that are invisible for our eye. There's a table which tells you how hot each of these images corresponds to, the temperature each picture corresponds to, and then there's another table that shows you which layers each of those pictures corresponds to. And if you think that, well, all this looks different just because of the colors, here's a black and white version, and you can see, yes, there's still a lot of differences that you can see. Some patches are bright in pictures and they're dark in other pictures, the same areas. And this is the wealth of information for us determining how the sun works. As I said, we also use wavelengths we can't see with our eye, such as ultraviolet, infrared, radio, and X-rays. And this particular picture shows you examples of that. On the top, we have X-rays, ultraviolet, and another form of ultraviolet called extreme ultraviolet. The middle row is all visible, and the bottom row is longer wavelengths, infrared, and radio. At this point, you might be asking yourself, well, what about below the photosphere? What about going inward to the sun? We've been talking about layers you can see from the surface of the sun on outward. There's lots of layers inward as well. There we cannot use light to study the solar interior. Light does not get past the photosphere. But we can use sound, and the sound which is trapped inside the sun. The sun is actually filled with sound, but there's only very specific tones that are present. So you can consider the sun to be a huge musical instrument. We can see these sound vibrations in the photosphere, and we use them to study the layers below the surface, and this is called helioseismology. These sound waves, the fact that the sun was filled with sound, were discovered a little over 50 years ago now, when observations were taken of the photosphere, and it was realized that the photosphere was moving up and down periodically, with a period of about 5 minutes. And it took about 15 years after that to figure out what was causing that. It had to be some sort of mechanical wave, by which we mean either sound or, like you see on the surface of the ocean. After much modeling and observing, it was finally deduced that these are indeed sound waves. The sound waves are caused by boiling, by the same thing that makes your tea kettle or your water in your saucepan make noise as it boils. I don't mean the whistle of the tea kettle. I mean the sound of it bumping and rubbing. The sun is boiling at its outer edge, and that sound is going everywhere, including back inwards. And there's essentially because the temperature changes as you go inwards, it gets hotter as you go inwards. Basically, you have a mirage is created. A mirage, very much like when you're driving down a hot road. You see down the road looks wet. That is because it's very hot near the road and it's reflecting back the light upwards. Same thing happens to sound inside the sun, and the upshot is you end up with only very specific frequencies that survive, and they are indeed trapped inside the sun. They fill the entire sun with a very specific pattern and a very specific set of frequencies or tones. Analogous to a piano has 88 keys, so you can make 88 different sounds. The sun has 5 million different sounds, which we can see and measure, and by very precisely measuring the tones of the sound, we can infer what the conditions are inside the sun as a function of the depth, for instance. So like we use light to look at the different layers going outward from the sun, we use sound to look at the different layers going inward in much the same way. Certain frequencies travel more deeply into the sun than other frequencies do. And by taking many of these frequencies and combining them, we can actually make images, sort of like holography in a way. And in fact, we do a form of acoustic holograms inside the sun. So now that you know a little bit more about how we learn about the layers of the sun, I think maybe you can appreciate that while most of the pictures we see of the sun looks very simple, it's a nice smooth sort of looking sphere with maybe a few spots on it, but in reality there's much more to it than we can see with just one wavelength. It's when you put in many different wavelengths or many different tones of sound that you can begin to be able to get all the details of why the sun is so fascinating.
Thank you, Frank, for that very insightful explanation of how we study the layers of the sun, both above and below the surface. We hope you enjoyed our webcast today. If you have any questions, please feel free to get in touch with us. You can get us on Twitter at @NatSolarObs. You can email us at outreach@nso.edu, or you can visit our webpage at www.nso.edu. We hope to see you next month, where we're going to be discovering the sun's magnetic fields.